Let's talk about the notion of primary decomposition of modules. So suppose I have a module M. So the setup is the following. Suppose M is a module over an integral domain R. Okay, so integral domain, remember, means that R is a commutative ring without any zero divisors. Okay, so if I have a module over an integral domain, then it makes sense to define the following notion. So here's a definition. So it's a subset of M, we'll call it Tor of M. This is the set of all elements M in M such that there exists element A in R, A is not 0, such that A acting on M gives me 0. So if I scalar multiply M by A, then I get 0 for some non-zero A. Okay. So the set of all such elements is denoted Tor of M. So observe, of course, 0, the element 0 of the module is certainly in Tor of M. And in fact, here's a little lemma. Tor of M is actually a submodule of M. So Tor M is a submodule. Okay, so let's check what does this involve. So we need to check that the well, it's closed under addition as well as under scalar multiplication. So suppose I have two elements M1 and M2 in Tor M. What does that mean? It means that there exists A1, A2, both non-zero elements of the ring R, such that A1 kills M1, A2 kills M2. And now the question is, so suppose I now want to show that M1 plus M2 is also in Tor M, for which I must produce an element, a non-zero element which kills M1 plus M2. Okay. So observe that there is a ready-made element which will do the job, which is the product of A1 and A2. So if I look at A1 A2 times M1 plus M2, so since the ring is commutative, I can switch the order of A1 A2 as I choose. So for example, in the first, so I'll use the distributivity property. In the first term, I will think of it as A2 A1 acting on M1, and the second term as A1 A2 acting on M2. Now A1 M1 is 0, A2 M2 is 0. So this is just going to be the element 0 of my module. The other important observation here is that this scalar A, which kills M1 plus M2, let's call it A, this guy is not 0. Okay, and why is that? Because both A1 and A2 were non-zero, and the ring was assumed to be an integral domain to start with. Okay, so this is an important observation here, since A1 and A2 are both non-zero and the ring R is an integral domain, A itself is not 0. Okay, so what does this imply? This means that M1 plus M2, this element, is also in Tor of M because it's killed by some non-zero scalar. Now similarly, we need to look at the next property, which is that if I am given, so this is the first axiom of being a submodule. Second axiom, so let's go to the next page. So if I take an element of Tor M, I need to show that any scalar multiple of that is also in Tor M. So I need to look at any scalar multiple, let me call it Sm. S is any element of the ring R. I need to prove that this is also an element of Tor M. Now if M is in Tor M means it's killed by some scalar A. There exists A non-zero in R such that Am is 0. Now observe that the same A will do the job. Now observe, this means that if I look at A acting on Sm by the axiom of the module axiom, this is As acting on M, but As is the same as Sa because the ring is commutative, and now that is the same as S acting on Am, and that's of course 0. Okay, so we keep using the fact that the ring is commutative, and also we use the fact that it is an integral domain. So what does this mean? So finally this proves the lemma, therefore the lemma is proved. So in particular it implies that Tor M is a submodule. Okay, now so we call element, so this is called Tor M is usually called the torsion submodule. Okay, this is called the torsion submodule of M. and the elements of Torem are usually called torsion elements. So if I have an element M in Torem, is usually called a torsion element. Any element of Torem is called a torsion element. Okay, so this is the first little definition and property that we need. Now, if M itself is torem, so this is the definition. If every element is a torsion element, so if M itself coincides with its submodule torem, then we say M is a torsion module. M is said to be a torsion module. Okay, and another little remark, another way of sort of thinking about this definition, torsion modules. So we can fix an element. So fix an element M in M and define what's called its annihilator. So the annihilator of that element M is all elements of the ring which annihilate it, all elements of the ring such that A acting on M is 0. Okay. So this is the definition, it's called the annihilator of M, and it's an easy exercise which I will leave you to do, that this is an ideal. So annihilator of any element is always an ideal of the ring, is an ideal. It's an ideal of R. Okay, so we have to use the fact that R is commutative in this case. So the annihilator is an ideal, and check, and the torsion elements are, so M is an element of Torem is another way of saying that its annihilator is not the zero ideal. It certainly contains at least one non-zero element. Okay, so this is another equivalent way of thinking about torsion elements. They are exactly the elements whose annihilator is not zero. Okay, now let me define the key objects that we will be interested in, which are called the primary components or the primary submodules. Okay, so this is like, well, the definition is very similar. So let's do the following. Let P be a prime element of the ring R. So R is an integral domain, and you know what the definition of prime elements are. They have the property that if P divides a product AB, then P must divide one of them. Okay, so if I have a prime element, then so throughout I'm making the same assumption that R is an integral domain and M is a module over R. We can define what's called M sub P. Okay, so what is this? This is almost like the definition of the torsion module. You take those elements of M which are annihilated by some power of P such that P power K annihilates M for some K greater than or equal to 0, greater than or equal to 1. Okay, so what does this mean? It's like torsion element, some sense. So observe the most obvious inclusion here. An element is an MP, of course, means it's a torsion element because it's killed by some power of P. Okay, and a power of P here, since P is non-zero, power of P can't be 0 also. Okay, so this is a special kind of torsion element which are killed by powers of the fixed prime P, and the key point here is that MP is also a submodule. So observe that MP is a submodule of Torem or M. MP is in fact a submodule. Okay, and why is this? Well, the proof is almost the same as what we did in the case of Torem. So I'll just quickly indicate the proof. Observe, if I have two elements M1 and M2, and if M1 is killed by some power of P to the K1 and M2 is killed by P to the K2, then in this case M1 plus M2 is certainly going to be killed by, well, certainly the higher of the two is enough. So I just need to take p raised to the maximum of k1 and k2. I don't even need to take the product. Okay, and similarly the other axiom. Okay, so it's a very easy quick check that MP is in fact a submodule. Okay, and this submodule is called the P primary component. So we usually call this so this is for the fixed prime P. This is called the P primary submodule or the P primary component of M. Okay, it's really a sub of Torem rather than all of M. Okay, now let's make a further assumption on R. So I'm going to make an additional assumption. Let R be a PID. Okay, a principal ideal domain, so which means not just an integral domain, but one in which every ideal is generated by a single element. Okay, so suppose I have distinct primes now. So let P1, P2, PR be distinct primes, pairwise distinct primes in the ring R. Now for each of them I can look at the corresponding P primary or Pi primary component. Okay, so look at MPI, which is all elements which are annihilated by some power of Pi. Okay, so these are the primary components. I claim that these submodules corresponding to distinct primes are, so then here's the little lemma, MPI, I goes from 1 to R, are what we will call independent submodules. Okay, what does independent mean? Well, this is something we encountered while talking about direct products of many submodules and so on. What it says is that the submodule generated by these are, by MP1, MP2, MPR, the union of these, that is just their internal direct sum. Okay, so let me write this out properly. So they are independent, i.e., what do I mean? Let N denote the submodule generated by their union. So let this be the submodule of N of M. Generated by these MPIs 1 to R. Now what is this really? So we usually write this like this: MP1 plus MP2 plus MPR. In other words, the submodule is, well, what does it comprise? Exactly elements which are of the form x1 plus x2 plus xr, where each xi comes from one of the MPI. So this is actually the collection of all sums x1, x2, xr, where each xi comes from the appropriate submodule MPI. So this is exactly the submodule generated by their union. Okay, so let N denote the submodule generated by their union. Then N is just the direct sum, the internal direct sum. N is actually the internal direct sum of these guys. This is what independence means. Okay, so independence is just saying that the sort of the sum of those submodules is actually the direct sum of the submodules. Okay, and if you recall what this direct sum means, going back to the lecture on direct sums and so on, this just says that if you take an element, so let's call such an element x, which is a sum of these xr's, then x can be written in this manner in a unique way. Okay, each element x in the sum of these submodules can be written as x1 plus x2 plus xr, where each xi comes from MPI in a unique manner. Okay, so i.e., so all this is really unraveling the definition of independence. I.e., what I mean is each x in N has a unique expression as a sum x1 plus x2 plus xr with each xi coming from the appropriate submodule for all I. Okay, so this is my definition of independence. Okay, so it's a lengthy definition, but the proof itself is very simple. So let's prove this. What do we need to show? We need to show that if x has two such expressions, then those two expressions coincide. Okay, so here's the proof. So let's suppose x, so let's pick an x in n. So let's take x in n, and if possible, if this guy has two different such expressions, x1, x2, xr, also y1, y2, yr, okay, where xi and yi come from MPI for all I, then, so as is standard in all these proofs, we subtract the two expressions. So this implies that if I take xi minus yi, so I call those as zi's, this means that z1 plus z2 plus zr is 0, where my definition of zi, it's just xi minus yi. Okay, and observe the difference of these two guys is also in the module MPI. Okay, so now I have this. Now from here I will try and prove that each of the zi's is 0, which is all I need. So observe that what are these zi's? Well, they all belong to the appropriate MPIs, means the following, means that some power of pi, so let me call that power ki, pi power ki kills zi. Okay, for some numbers ki's greater than or equal to 1. Okay, so what does this mean? So let's start out. I want to prove that z1 is 0, for example. Okay, so to do that, let me do the following. I will multiply this left hand side by p2 power k2, p3 power k3, and so on. Okay, so let me start here. So what do I mean? z1 plus z2 plus zr is 0. So let's multiply both sides of this equation by p2 power k2. This is a scalar now, this is an element of the ring. This is a scalar that I want to use. Okay, so this acting on z1 plus z2 plus zr is 0. Now observe that if I look at the other terms z2, z3 till zr, each of them is killed by an appropriate power of p2, right? So this scalar p2 power k2 till pr power kr, it kills all the terms in this sum except for z1 itself. Okay, so all the other fellows are 0. z1 alone survives. It's p2, p3 till pr power kr acting on z1 is 0. Okay, now remember, however, we also knew that z1 was killed by p1 to the power k1. Okay, so these are my two equations which will tell me that z1 itself must be 0. Why is this? Because observe, these two equations are of the following form. It says that z1 is annihilated by two elements. Okay, so what does this mean? It says that p1 power k1 belongs to the annihilator of z1, and the other product p2 k2 till pr kr also belongs to the annihilator. Okay, but remember these two elements p1 to the k1 and p2 p3 pr to the corresponding ki's, these two elements are relatively prime, right? They don't have any common prime factors here. So what does that mean? So if you recall from the lecture on PIDs and so on, this means that, so but the GCD of these two elements is 1, means that the ideal generated by them, so look at the ideal generated by these two elements, this ideal is just the whole ring, it's the ideal generated by 1. Okay, so what does that mean? In particular, it means that, so remember I've already said, let's go back here, I've said p1 to the k1 belongs to this belongs to the annihilator and this belongs to the annihilator. Okay, which means that the ideal generated by the two of them is a subset of the annihilator. Okay, so but then that ideal is the whole ring R. Okay, so which means that the ring R itself must be the annihilator, right? So but remember, I know that this ideal generated by these two elements must be contained in the annihilator of Z1, which means that the annihilator is the whole ring. There is no other way out. In particular, it means that the specific element 1 annihilates Z1, which means that 1 must annihilate Z1. What does that mean? That just means Z1 is 0. Okay. Now the same proof applies to the other elements. You can just replace Z1 by any of the other Zi's, multiply by the product of all the prime factors other than the ith prime factor. Okay, so the proof works similarly for the other cases. Okay, so that's the end of the proof. So what have we proved? If you take the primary components corresponding to distinct primes are always independent, meaning their sum is actually the direct sum. Okay, now that's one thing done. That's an important statement. And now here's the main theorem that we shall be interested in, okay, which concerns primary components. So if I have R, so I'll put in a few more assumptions now. If R is a PID, that I already used, and M is a R module, but I need some more adjectives. I want M to be a finitely generated torsion module. So remember, torsion module means every element of M is a torsion element. It's killed by some non-zero element of the ring. So I've thrown in these two adjectives. It should be finitely generated and it should be a torsion module, okay, over this ring R. Then if R is a PID and M is a finitely generated torsion R module, then two statements. One, these primary components MP is 0 for all but finitely many primes, for all but finitely many. So notice that the ring itself may have infinitely many primes, for all but finitely many primes P of R. Okay, the ring may have infinitely many primes, but we are saying that the primary component MP will be 0 for almost all those primes, okay, except for some finitely many of them. And statement 2, so let's give these primes a name, for all but finitely many primes P of R. So let's call these primes P1, P2, PR, for all but finitely many primes, say P1, P2, PR. So I'll just give the primes a name of R. Okay, so MP1, MP2, MPR are the only ones which are non-zero, and property 2 says M is actually the direct sum of these MPIs. You take the non-zero primary components, whichever primes give you non-zero answers, and the direct sum of those primary components is actually the whole module M. Okay, so we've already developed many of the ingredients we need for this proof. So observe that M is finitely generated. So I'm going to use all my hypotheses. So first let x1, x2, xr, maybe not the same r, xn be generators. Okay, so remember, finitely generated module just means there are finitely many elements such that the submodule generated by these finitely many elements, by the set of these elements, is the whole module. Okay, so let x1, x2, xn be generators of M. What does that mean? In other words, M is just the span. Okay, to use a vector space term, this is just all elements of the form Ci, Xi, linear combinations of these generators. The set of all such elements will give you the entire module M. Okay, now this is the first assumption, that it is finitely generated. Now let me use my second assumption. I'm also given that M is torm. Okay, that M is a torsion module. In particular, it means that each of these generators is a torsion element. Okay, so which means that each generator Xi is has a non-zero annihilator, right? It's got at least one non-zero element which annihilates it, And remember, in this case, I have assumed that R is a PID, right, a principal ideal domain. So, and recall I already mentioned the annihilator is a ideal of my ring R. Okay, so it's since the ring is a PID, this ideal must be singly generated. Okay, there must be a principal ideal. Okay, so the annihilator looks like this for some di which is not 0. Okay, so I've used the fact it's M is torsion and R is a PID. So both assumptions have been used in this step. Okay, and this is for all I. This is for all I equals 1 to n. Okay, now where are we going to manufacture these primes from? What are those finitely many primes? They are going to come from the di's. Okay, so look at the di's. I have a principal ideal domain which if you recall is also a unique factorization domain. I can factorize every element of R uniquely into a product of powers of primes. So I look at this prime factorization of all the di's. Okay, so consider each di has a prime factorization. Each di has a prime factorization. So I can look at all the primes which occur in the factorizations of all the di's. Okay, so that's going to be my my set of primes. Okay, so consider the set P. So consider P prime of R such that P occurs in the prime factorization. In other words, P divides di for some I. Okay, so I will take the union of the prime factors of all the i's. So for some I from 1 to n. So take the collection of all primes which divide the di's, and this is only a finite set because there are only finitely many di's, and each di will have some finitely many prime factors. Okay, so this full collection of primes which I get, let me call them P1, P2, PR. Okay, now consider these MPIs. The claim is that M is actually the direct sum of these MPIs. Okay, so I am going to prove the second part of my theorem, which is that I can find finitely many primes such that M is the direct sum of those guys. Then I will show that for all the other primes NP is actually 0. Okay, so M is the direct sum. That's the claim. Okay, so let's try and prove this claim now. Okay, so recall we have already shown independence. Okay, so which means that I know that these MPIs, their sum is equal to the direct sum. That I have already shown. Okay, so proof, recall, we already showed independence, meaning the submodule generated by these components is actually a direct sum. Okay, so what remains to show is that this sum MP1 plus dot 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 MPR, this is equal to the whole module M. Okay, so I need to show that every element of M can be obtained as a sum of elements x1 plus x2 plus xr coming from the corresponding MIs. Okay, so only remains to show that each element of M lies in the sum MP1 dot 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 MPR. Okay, and in fact I don't need to worry about every element of M being the sum. It's enough to prove that the generators belong. Okay, because if once the xi's belong, then every other element is after all linear combination of the xi's, right? So they would also automatically belong. So it's really a question of showing that the generators belong. So let me just say I don't even need to do this. I can actually do something simpler. I can just show that the generators xi only remains to show that xi lies in this sum for all I equals 1 to 1. Okay, so this is a simpler step. So let's try proving this. Okay, so now to do this we need a little lemma. So let me state my lemma first. So I need to show every generator belongs. So here's an intermediary step. It's a lemma. Let A be a non-zero element of R. Okay, and suppose I have an element of M which is annihilated by A such that AX is 0. Okay, now if A can be written as a product B times C, suppose A can be written like this with B and C relatively prime. Okay, so I'm able to split A into two pieces and the two pieces are relatively prime, then I can split X into two pieces as a sum of two pieces Y and Z with the following property that Y is killed by B and Z is killed by C. Okay, so where what are Y and Z? Also elements of I should have said with Y, Z belonging to M. Okay, so what is this proposition? It's an interesting statement. It says that if X is annihilated by A and A can be split into these two pieces, well, split now means as a product of two relatively prime elements of the ring, then the element that it annihilates, the element X, can also be written as a sum of two elements Y and Z, where Y is killed by one part of A, that is by B, and Z is killed by C. Okay, so it's an interesting little statement and the proof is rather simple. So observe that since A can be written as BC with B and C 1, so all this is under the same assumption as my theorem that R is a PID. So observe as before, GCD of B and C is 1 means that the ideal generated by B and C is the whole ring, which means the ideal generated by BC is 1, the whole ring, which implies in particular that I can write some 1 as a linear combination for some R and S belonging to the ring R. Okay. So this is the important property that we keep using. Now observe that, so this is where my splitting is going to come from. So my element X, which I want to split into two pieces, I think of it as 1 times X, and 1 I write as RB plus SC acting on X. Okay. So what is this? This is RBX plus SCX, and these are going to be my Y and Z. Okay, so let me define Y and Z here. So this fellow here is going to be Y. So I will define Y to be this element and I will define Z to be this element. Okay, so these are my definitions. So we need to check that these two elements do the job. What does that mean? Well, of course their elements of M is clear, but let's check that they are annihilated by B and C respectively. Okay. So for Y, let's check. Suppose I hit Y with B. What is BY? Well, this is B acting on SCX. Okay, but now I can use my properties of the module, the axioms of a module. This is BSCX, and use the fact that the ring is commutative. Think of it as SBCX, and SBC is just SAX. Okay, because BC is A and AX was 0. Okay, so this just shows that BY is 0, and the proof for Z is similar. So you hit C on RB and then combine the B and the C together to get an A. So this is the same proof. Okay, so we are done. So what this means is that if you have A as a product of BC, then X can also be similarly split in as Y times Z, Y plus Z. Now why is this interesting or important for us? Because we are trying to show the following, that each element Xi lies in this sum, right? What that means is I need to be able to split Xi into several smaller pieces. I need to be able to write Xi as a sum of an element from MP1 plus another element from MP2 and so on till an element from MPR. Now this splitting comes because of this lemma. Why? Because the element X1 is killed by some element Di, right? So now observe, let's go back to the proof of the theorem. So let's now complete back to the proof of the theorem. So let's do the proof now. Back to proof of theorem. So what we need to do here is to say, let's look at this element xi. It's killed by di, right? That's the property we started out with. But di, it can be written in terms of its prime factorization. So I just factorize di. So what is di? It will be some prime. So well, we have called those primes p1, p2, pr. So maybe I will just use that. So let me say di looks like p1 to the k1. Okay, so just do this. So I mean the i's and so on are not so important. Anyway, so let's do this. So p1 to the k1, p2 to the k2 till pr to the kr. Okay, and now of course not all the primes will occur in the factorization of all the di's necessarily. So I will just say the ki's could be 0 or some number greater than or equal to 0. So I take the prime factorization. The key point is that only p1, p2, pr can occur. None of the other primes can occur in this decomposition, because that's how I define my primes. I took the di's, I factorized each of them, and I collected together all the primes that result. Okay, so the di is this product. Now what does this imply? Now let's use the lemma. So by the lemma, so I'm now going to first split this di into two pieces. I will look at p1 to the k1 and the rest. Okay, so I will think of this as my a. To apply the lemma, I will think of this as my a, this as my b, and this element as my c. Okay, b and c, remember, are relatively prime. A is a product, and a, which is di, kills xi. Okay, so now by lemma, what can I do? I know that xi can be split into two pieces. I can write it as, so let me just call it for now y1 plus z1. y1 is killed by b, z1 is killed by c. Okay, so I split into two pieces. But c itself is again a similar sort of thing. It's a product of the remaining primes from p2 onwards. Okay, now I can repeat the analysis with c. What do I mean by that? So here's what we will do. We will think of z1, c z1 is 0. Start with this equation. Apply the lemma again to c. Okay, so what does c look like? It's this product. Again, I split into two pieces. So let's try using some other color. So this first term alone is separate. The remaining terms are separate. Okay, so when I write c, I will think of writing c as a product of p2 power k2. So maybe I'll just do this here. C can be written as p2 to the k2 is one term, and all the rest is another term. Okay, and these two are relatively prime. Again, apply the lemma. It says that if c kills z1, then z1 can be again split into two pieces. So let me call this y2 plus z2. Okay, now what property does it have? So I've replaced this equation by there is an element called y2 which is killed by p2 to the k2, and there is the element z2 which is killed by the product of the remaining prime factors. Okay, now repeat the process with z2. z2 again will split into two pieces, y3 plus z3. This will split into two pieces, y4 plus z4, and so on. So this is some sort of inductive procedure. Okay, so what are you finally doing? You are successively splitting this xi into smaller and smaller and smaller pieces. Okay, so I hope you are convinced that what we get at the end of this process is the final equation. This xi here has been written as y1 plus y2 plus yr, where each yi has the following property, that yi or yj is killed by the corresponding some power of pj. So pj power kj acting on yj is 0. One to r. Okay, and this implies that yj's belong to the corresponding m pj's. Okay, so this completes the proof, because what we have done therefore is to show that each of the generators, so recall this is what we needed to show here, that each of the generators, each element xi of m lies in the sum of these elements. Okay, now there was still the other part of the theorem which we needed to prove, right? Let's go up. So we have done this, show that m is actually the direct sum, but why are all the other MPs 0? Okay, let's just prove that the remaining MPs are all 0 as a consequence of what we've just proved. Okay, still need to show the last bit of the theorem. Now let's claim if P is not one of the PIs, then MP must be a 0. Okay, why is this? Well, again, let's see proof. Suppose I have an element in MP, suppose X belongs to MP. What does this mean? It means that it's killed by some power of P, right? P power k x is 0. For some k greater than or equal to 1. Now, we have already shown that x is just the direct sum of the MPIs. So let me first write x as x1 plus okay. So we can write x as a sum x1 plus x2 plus xr, where each xi comes from the corresponding MPI. Now p to the kx is therefore p to the kx1 plus dot 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 p to the kxr. Okay, and this is a 0. That's our assumption. Okay. Now observe that each of these terms p to the kx1 is in the first module MP1, right, because it's just x1 multiplied by some scalar, and this guy is in the final module MPR. And what are we obtaining here? That a sum of elements from these different submodules is a 0. Okay, but we have already shown that these submodules are independent, which means that if the element 0, if it can be written as a sum of elements from these modules, each of those components must be a 0. Okay, so this means by the independence of the MPIs that each of these p to the kxi is 0. Okay, for all I equals 1 to r. And why is this? By the independence. Okay, now again we are we just repeat the familiar argument. What does this mean? It means that p power k belongs to the annihilator of xi. Okay, we also know that the annihilator of xi is di. Okay, so what does this mean? This says that p to the k is in the annihilator, and so this means that we can complete the proof in one of two ways. So observe that p to the k and di are relatively prime here. Just to repeat the sort of argument we have used before. So observe p to the k. So remember, p is not one of those primes which divides di. So p to the k and di are actually relatively prime to each other, which means that both p to the k and di are elements of annihilator of x. So this means that the ideal generated by p to the k and di must be the whole thing, but both of them are in the annihilator. So this means that the ideal generated by them is in the annihilator, and like we already did before, this means that xi is 1 is in the annihilator, which means xi is 0, which is a contradiction. So we assume to start with that xi was a non-zero element. They are the non-zero generators. Okay, so maybe I didn't put that into my initial step of the proof. So let's go up. Be non-zero. There's no point in taking a 0 generator here. Be non-zero generators of M. So these di's are not units. So this is not the whole ring here. Okay, so that completes the proof of this theorem. So this is a very interesting and important theorem. It says that when you have a finitely generated torsion module over a PID, then torsion means everything is killed by some element of the ring, but it's actually enough to just look at prime power elements. Okay, just look at things which are killed by powers of some primes. Okay, and only finitely many such primes finally matter. All the other guys are 0, and those finitely many primes will, you know, they will sort of the primary components of those, when you take their direct sum, that will give you the whole module M. Okay.